All right, we are live. Hello YouTube. Hello everyone. Yes, we have returned. SwagTestPrep, as you might know, has been working with our friends, and we have decided that, upon request from a lot of our viewers, that it's time to expand. While all our history videos are good, we realize that we're only gearing to a specific audience. Now, we know that people are not only struggling with history, and there's other academic subjects that people really need help in, right? One of the main subjects that I find that people sort of need a little bit of extra help in that they can't get from just like regular classes is calculus. Calculus is one of the hardest subjects that a student can take in high school, and for this we have opened up a new chapter in our philosophy, and now from today we'll start doing periodic videos on calculus tests, calculus topics, where the same way we did with history, you can ask us questions, message our the person that we have for you. So now let's go into that. So SwagTestPrep, specifically me, I've chosen a gentleman who is very qualified and thinks he can definitely handle this large task. Making videos on calculus is very different from history, and me and Josh would have loved to do this, but we just do not have time in our schedule to dedicate to history, our academic school stuff, our extracurriculars. So we have found this gentleman who thinks that he will easily be able to, oh, there he is, you can see him, who will be able to do this for us. So I would like to introduce Mr. Ganesh Gopal, who is ready today to talk about calculus, specifically our chapter, the test, as we know, coming up. It's coming up tomorrow, depending on whether or not we have a snow day, early dismissal, whatever. But with his help, we hope that you'll be able to learn area and solids of revolution, which is the topic for this test. And from this point, I'm going to turn it over to Ganesh, and he's going to talk a little bit about himself and give you a little bit of his philosophy, maybe some of his qualifications. So Ganesh.
Hey guys, I'm Ganesh, and I just want to start off by saying that this is new for me, just as it is new for everybody else here, so I'm going to make mistakes, and I hope that you forgive me as I do so. But the overall goal of this would be just to give you guys a better understanding of what it is we're doing, and hopefully it'll help out. I think that I have a good grasp on the concept at hand, and I really hope that through these videos you learn and you are able to more clearly express what you want to do on the tests, therefore getting yourself more points. So, Rahul, is it okay if we begin now, or?
Yeah, sure. One thing I would like to point out before we start is a lot of times what the issue that arises is people say that, like, oh, we're watching your videos, like it's helpful and all, but there's no real like difference that we see coming out of this. And to this I would like to say is that by keeping on and like hearing more and more on the subjects, what slowly happens is that you get a more of a natural talent for it. So even though, like, for example, with history, if you already have memorized the chapter, you already have memorized certain facts and things, by hearing different people talk about it, it really helps your mind to get a more like a 360 view of the subject. So Ganesh, he's going to take a similar approach to your calc teacher, but he will give you a new view, which will hopefully develop your idea on the subject a lot better than it has been. So yeah, Ganesh has told me he's ready to go. I'm going to turn over the broadcast to him, and from here he will be using his different softwares to integrate calculus into this video. All right, thanks for watching. Don't forget to like, favorite, and subscribe. At the end of this video, tell Ganesh how you think, and through this process, if you feel like you want a shout out at the end of the video, either comment on this YouTube video or message me on Facebook, and we will make that happen at the end like we did with the last video. We'll just recite out a bunch of names of people who feel like they deserve a shout out. Obviously, you can ask questions to Ganesh. You can comment in the YouTube comments, or you can message him on Facebook. But from here, I'm going to turn it over to Ganesh, and Ganesh, it's all yours. I will be going off. So good luck.
All right, thank you, Rahul. Okay, just to start, Rahul, are you still there for a second?
Yes, I am.
Can you see my screen?
Yeah, it's
Okay.
it's good.
Okay, good. All right then. So let's just get right into it. I'm going to try and waste as little time as possible. Okay, so today's lesson we're going to be focusing on 4 different key concepts that are going to be covered on the test. First is going to be area bounded between 2 graphs. Second is going to be solids of revolution. Third is cross sections, and the fourth is arc length. So without further ado, let's jump right into area bounded between 2 graphs. So let's suppose that this is, oh sorry, excuse me for a second. This right here is our y-axis of a graph right here. Great, and this right here is our x-axis. Okay, so let's begin the graph. So let the green function here be represented by, say, just f of x. And then the blue function here be represented by g of x. Now, what our objective here is to find the area bounded between f of x and g of x. Now, we know that the area beneath curves is simply the integral of that curve. However, in this case, what we are interested in is this area right here in the yellow. So for that case, we would do something very simple, which is simply the area of this minus the area of this, which actually turns out to simply be the integral of f of x minus the integral of g of x dx. Now, it's important to place limits on this. Suppose this is 0 to start, and this is b over here. So it's just from 0 to b of the integral of f of x minus g of x dx. So this is just the broad general definition of it, and it can get a little more complicated if you decide to revolve it, or sorry, not revolve, if you decide to find the area between curves that may look more like perhaps a sine curve going like this, with maybe another curve going like this. And in this case, you have to be careful. It's always going to be top curve minus bottom curve. So in this case, suppose that this function here is f of x, and this function here is g of x. You're always going to do here f of x minus g of x. For this area right here, it's going to be, for this curve right here, it's going to be g of x minus f of x. For this curve here, it's going to be f of x minus g of x. And for this curve, it'll be g of x minus f of x, and then you can decide to bound it off at wherever value you decide to choose. And for this case, you would actually need 3 separate integrals, so it's important to keep that in mind. Okay, so let's see if we can just go ahead and clear the board real quick. Cancel, sorry. And let's give a practice problem a shot. For this, I encourage that you pause the video, and as you pause the video, go ahead and try the problems that I'm going to show you here before I actually do them, so it's better for you to get understanding. So the first problem that we're going to try with this is going to be f of x equaling cosine of x. And g of x, let's do a different color, g of x equals, say, negative x minus 4 squared. Okay, so now what you want to do is find the area bounded between these 2 curves. So at this point, you can go ahead and pause the video, give it a shot if you want. If not, then let's just go ahead and get right to it. So once again, let's draw our axes here. That would be our y-axis, and this would be our x-axis. So the curve f of x equal cosine of x, it would look something like this. It would just go up, oh, excuse me for a second, go up like this, down, and back up. And then the curve of g of x would look something like this. Suppose this is 4 right here because that's the root of this function. It would look something like this. Now the area we're interested in is the area in red. Okay, so originally if this was a non-calculator problem, what you would do is you would set these 2 equal to each other to find these intersection points. However, that's kind of tedious to do by hand, so it's better if we use technology. So for now, we'll just label this point A and point B for the x values. And using a calculator, it's easy to figure out that point A comes out to approximately 3.00469, and point B comes out to approximately 4.478. So now you want to find the area between these curves. So using our formula that we had last time, it would just simply be top minus bottom. So in this case, it's negative x minus 4 squared. Sorry, the x goes here. Negative x minus 4 quantity squared. Now it's minus bottom, so minus cosine of x dx on the outside, which goes to the entire thing on the inside. Okay, so the a and b would just be the bounds you found right here. Now, if I was to evaluate this integral, let's do the calculator syntax. So, because it's important to know this for the test as well. So, say you set y1 equal to negative x minus 4, or maybe I should just say, sorry, f of x. All right, and then y2 is equal to g of x. Okay, so on the TI-89, the calculator syntax would look something like this. Just gonna have a little integral sign here, and then parentheses y1 x minus y2 x. And then you're going to have a comma x, comma, and I'm just going to put a and b for these, but you'd actually enter the values for a and b, and then close it. And if you work that out, it actually comes out to about 0.744061. So that is actually the area in red right here that we're interested in. So that was a rather simple problem, but you might see one like that in the test, so just be sure to keep your eye out for it. Let's go ahead and clear the graph again. Okay, so the next concept that we said we'd talk about was solids of revolution. So for solids of revolution, the approach is very similar to any kind of regular integral setup that you might have. Let me just draw an arbitrary curve here. Suppose it's just the graph of y equals x squared. Okay, so it's y equals x squared. So now what we want to do is we want to take this graph and we want to rotate it around the x-axis, right here, the x-axis. Say from 0.0 to 0.4, for example. So I'm going to do this in a different color. It would look something like this, the curve. It would go downwards, and then you'd have like a little opening right here, and then this would all just be shaded in. And the way we can actually approximate that area is by taking an individual rectangle underneath this curve and just flipping that around the x-axis, thereby forming a disk. A disk. So the volume of any disk, like if I just give you any kind of disk like this, arbitrary disk, the volume of this disk would just be pi r squared, correct? But in this case, what is our r? Our r in this case would be the distance from here to the distance from here, which is our r. So that would actually just be f of x, which is x squared in this case. So the formula for this method is just going to be pi times the integral from a to b. You got to keep in mind your a to b over here. A to b of f of x, but now it's squared, so it's quantity squared dx. Now that might seem very interesting, and you're like, okay, well this curve is nothing special to me, like it means nothing to me, but it's interesting because you can actually use the disk method to find areas for underneath curves that you may think we just take by heart. For example, if you were to look at a sphere, right? I'm just going to do my absolute best attempt at drawing this. Something like that. A sphere, right? The volume of a sphere, just as we know, is going to end up being 4/3 pi r cubed, right? But you might be asking yourself, well, how do we get that? Like, there's no intuition behind that. But we actually use the disk method for that, and we can do that as a practice problem here because, well, first off, you want to find the equation for a two-dimensional version of a sphere to rotate it, right? And two-dimensional version of a sphere is nothing else but a circle. And the equation for a circle, as we know, is x squared plus y squared equals r squared. But unfortunately for solids of revolution, it has to be a function that you're revolving. So let's go ahead and solve for y. If you solve for y, it comes out to radical r squared minus x squared. And this is the thing you want to rotate. And this is only half the circle, keep in mind. It's not plus or minus. It's only half the circle because we don't need the other half. Because if we're just rotating it around this line, then the other half is negligible. And also, you can't rotate something if the axis of rotation is right in the middle of it. You can only rotate one side of it. Similarly, we're only rotating one side of this. So let's go ahead and give it a shot. So this is going to be negative r and r. So let's set up our integral that we typically get. It would be the integral from negative r to r. Now it's pi times that integral because of the disk method that we're using. And there would be f of x, which in this case is radical r squared minus r squared. But keep in mind we're squaring that quantity because the area of a circle is pi r squared. So here for pi r squared, if you square this, you're left with nothing but r squared minus x squared, but you're going to have a dx on the outside. Now let's just go ahead and try and integrate this now. So this would be pi times, now the r squared is just a constant, so if you have, say for example, you have the integral of just like say 4, that would just be 4 times, sorry, dx here, that would just be 4 times x because it's just a constant. So here it would just be r squared times x, r squared x in other words, and the integral of negative x squared would just be negative x cubed over 3. And that's just from the reverse power rule. And now we got to keep in mind this is going to be going from r to negative r. Okay, so let's go ahead and try and evaluate this. Let's see if I can make some more room for myself. Okay, so let's evaluate this. Pi times, now we plug in r for x, we have to keep in mind, r for x. So this becomes, just plugging in r here, becomes r cubed minus, now it's going to be r cubed over 3. Correct? And then you want to subtract the negative r. That's just the fundamental theorem of calculus in evaluating integrals, top bound minus the bottom bound. So now you subtract, careful to put parentheses here, now you plug in a negative r. This is going to be, if you put negative r times r squared, that gives you negative r cubed, correct? And then if you put in a negative r plus, sorry, negative r for the x cubed, it's going to give you negative r cubed, but you have the negative here already, so it's going to give you plus r cubed over 3. Okay, so this becomes pi times, now let's go ahead and combine like terms here, r cubed minus a negative r cubed, so that's going to be plus an r cubed, so 2r cubed, now minus r cubed over 3, and the minus distributes to the minus over here as well, so minus r cubed over 3 again, so minus 2r cubed over 3. And this is what we have so far. Now, we have to give a common denominator to subtract these two, so let's go ahead and do that. So this would be 6r cubed over 3 minus 2r cubed over 3, all times pi, of course. Now maybe a little drum roll right here as we're on the home stretch here. So 6r cubed minus 2r cubed is going to yield 4r cubed over 3 times pi, which can simply be written as 4/3 pi r cubed, which is the equation we all know and love for the volume of a sphere. Okay, so going on. Now that we've established what solids of revolution are, let's go ahead and do a different technique that people use for solids of revolution. What we just did was known as a disk method, but what we're just going to do is going to be called the washer method. Now the washer method is very, very similar to the disk method, except you basically just have two disks embedded within each other, and you're interested in only the area in blue, for example. So it's going to be the outer radius minus the inner radius. But you have to keep in mind the properties of integrals, so you have to make sure you're squaring it, you have to make sure your bounds are correct. So just the general equation for it would look something like this. It would be the integral from a to b. And now, of course, you can't forget your pi on the outside, because we're still doing the disk method, essentially, which is two disks now. And now, this time it would be f of x squared minus g of x squared dx. Now the dx goes to the whole thing, keep that in mind. So the f of x in this case would be our outer, and the g of x in this case would be our inner. Just make sure you always think outer, inner, and then you should be good, because you just always have to have some more practice with that. Now I will do a practice problem with this one, but I'm just going to go over the shell method as well and see if I can integrate both of them into a single practice problem. So just bear with me for a moment. So the next method, real quick, is called the shell method. Now, it's important to note that this is not necessary to know for the AP Calculus exam. It's only necessary, for example, if they give you a really hard washer method rotation problem and you believe that you can just do it using this method instead. But just wanted to point out, it's not going to be on the AP exam. So the washer method, the cylindrical shell method is basically rotating against the grain, as what my math teacher likes to call it. So, for example, what we've been doing so far has been we've been rotating a vertical rectangle, about this way, basically forming an easy to get geometric shape, which is just a disc, and we call that with the grain. But suppose that we were to rotate it this way, right? If we rotated it that way, it would be we couldn't use the same disc, is what I'm saying. We would have to use shells. Shells would look something like this kind of, except they would have a depth to them, like that, cylindrical shells. And if I was to just flatten one out, it would look like this. And now flattening out is important, because this is actually how you get the equation for cylindrical shells. So suppose this is our function f of x right here, right? So the radius, right? The radius of from here to here would be considered the radius, because you're revolving it around the y-axis. So the radius of your shell right here, because that's your little shell right here. So this is going to be radius r. But what is your radius r? Your radius r is actually just simply your value of x. As long as you're rotating just around the y-axis, your radius is just going to be x. So if your radius is just going to be x, right, or yeah, just x in this case, then what's your entire circumference going to be? Because when you flatten it out, well, we know that the circumference of a circle is 2 pi times the radius, or pi times the diameter, whatever you prefer. So in this case, since our radius is r, it's going to be 2 pi r. Now r is the same thing as x, so it's going to be 2 pi x. And our height, now this height is a little bit different. It's just the height of the rectangle here. The height of the rectangle is going to change considerably based upon how your function is changing. So our height of the rectangle is just going to be f of x. So now that we know this, we can establish a relationship between them in the form of an integral. So say from point A to point B, we're trying to take this thing and rotate it around the y-axis, right? So it would be the integral from A to B. Okay, but now the area of this kind of like thing that we've rolled out after getting the shell is going to be this times this. This thing times this thing. That's just length times width for rectangles. And the 2 pi is just a constant, so we can pull that out. 2 pi times x f of x. And that's it. That's all there is to the shell method, really. It's just 2 pi times x f of x. There's no squared or anything. However, if you would like, even my math teacher recommends this sometimes, is you can take the 2 pi and you can put it on the inside of the integrand. It makes no difference, but it can help you remember which method it is you're using. So for example, if you know you're using the disk or the washer method, put your pi on the outside. But if you're using the shell method, then go ahead and put it on the inside, just to remind yourself what it is you're doing, in case that helps. So let's go ahead and tackle a challenge problem. It's actually not that bad. It's pretty straightforward. So let's just go ahead and draw our axes once again. There to there, and there to there. So I'm going to give you two functions, and what I want, sorry for 1 second, what I want is, I want the area between them to be rotated around the y-axis. So these are two functions, y equals x to the 1/3, and y equals 1 over 4 x. Okay? Just like a visual aid here, it would look something like this for y equals x to the 2/3, I'm sorry, x to the 1/3, and 1/4 x would look something like, different color, sorry, something like, no, not blue. There, something like that. And that's supposed to go through the origin. I know that's a really terrible visual, but just to give you an idea of what it is we're dealing with. Now, I'm sorry, I said over the y-axis, but actually, let's make the problem a bit more interesting. Let's rotate it around the line x equals pi. Okay? And the reason I chose pi specifically is because you might be using pi for some of these methods, and it's important to not screw this pi up with that pi that you're going to be using. So let's begin with the washer method, actually, the washer method. So let's do this in a different color down here, black. What we want, essentially, is to take this area right here. Is it going to shade for me, maybe? Let's see if it shades for me. Good. Okay, so you want this area right here, and you want to take that over the line y x equals pi. So using the washer method, we know that to be outer radius minus inner radius. So the outer radius in this case would be our blue function here. Now our blue function is going to be y equals x to the 1/3. But you got to keep in mind, the rectangles here that we're setting up aren't going to be vertical. They're going to be horizontal, because this function minus this function horizontally. So to keep those things in order, what we have to do is we have to solve for these functions in terms of y. And that's simple enough to do, because x equals y cubed and x equals 4y. That's an important step, because if you put in x to the 1/3 or 1/4 x, this integral won't work out as properly as it should, because you're rotating with the grain in this case. So you're going to have to do horizontal rectangles. So let's go ahead and give it a shot. So using the washer method, just to make that nice and clear, washer. Okay, so the outer radius. Okay, just start with the outer radius is going to be the 4y here. So 4y. But now we have to keep in mind, the outer radius isn't just going to be 4y by itself, because that would just be if we were rotating around this axis. We're rotating it around the line, x equals pi. So we'd have to subtract, basically, a negative pi from here. So let's see here. 4y plus pi is what we'd get. Oh, excuse me, sorry. This should be a negative pi, but hopefully the graph made that clear. But it should be a negative pi, because we're on the left side of the y-axis. So this is going to end up being 4y plus pi, and that's going to be our outer radius from the blue function all the way to our axis of rotation, which is our outer. And then we're going to square that. And then we're going to subtract our inner radius, which is going to be y cubed in this case. And this time we have to add pi again, because we're still rotating about that line. And then quantity squared dy this time, not dx. Now we have to choose, what are our bounds on this integral going to be? Okay, so our bounds are going to be where these two lines intersect each other. So they obviously intersect at the origin. That's one spot. So I can immediately put 0 as one of my bounds. Now what's the y-coordinate for where they intersect? Well, let's go ahead and solve for it, because you get x to the 1/3 equals 1/4 x, correct? So go ahead and do multiplication here. You get 4x to the 1/3 equals x. And then 4 equals x to the 2/3. And then 4 raised to the 2/3 gives you x. Now 4 squared, actually no, maybe I should do, no, that'll be fine. But then what this works out to is 4 to the 2/3 works out to give you the point 2. So now that you know the point 2, because 4 squared gives you 8, and then the cube root of 8 is 2, which is how I got the 2 up here. And then now that you know that x is 2, well, what's y going to be? You can plug into either one of these functions, right? So if you get x is, oh sorry, excuse me, I'm sorry. This is going to be 8, because it's going to work out to give you 8. And then your x, if you plug in for your x value, 8 to the 1/3, this comes out to 2. So I mixed up the x and y for a second there. So this point comes out to 8, 2. Okay, so now which one of these points are we going to use for our integrand? We're going to use 2, because we're putting it in terms of y. So this right here is going to be our integrand. The integral from 0 to 2 of this squared minus this squared. But now we're forgetting one important part, which is the pi on the outside. Because we are doing the disk method, in essence, one disk minus another disk. So because we are doing the disk method, we are multiplying by pi on the outside. So this integral actually takes a while to do by hand. If you want to do it, I go ahead and I encourage you to do it. However, the answer comes out for this one, if you were to plug it in on a calculator, it comes out to 8 pi times the quantity, 21 pi plus 64 divided by 21. Okay? So that's the washer method for doing this thing. Now let's go ahead and employ the newer method we use, the one that's not going to be on the AP exam, which may actually make it a little bit easier. Let's get rid of all this. Okay, so suppose we had our same exact Same exact function here. I'm going to use the straight line. Let's hope I can draw a straight line here. There. Okay, so same exact function. Something like this for our x to the 1/3, and this is something like this for our other bound. So let's go ahead and fill that in with the blue area. Okay, so now I'll label this y equals x over 4, right? Because that's the same as 1/4 x. And this equals x to the 1/3. So now that we have these two functions, we're going to try to do the washer method now. Now same axis of rotation as well, x equals -pi. So using the shell method in this case, because we're going against the grain, we're going to have just regular triangles here, regular vertical triangles here, and then we're going to rotate that around. So the regular vertical triangles, we're going to keep in mind that key concept of top minus bottom. It's always going to be top minus bottom. So keeping that in mind, it's going to be x to the 1/3 in this case minus x over 4. So this is going to be our top minus bottom, x over 4. And then, now we want the radius. So this is a little bit more tricky, but it's not terribly hard. The radius, right, between here and any point that you're going to do here, well, let's break it up here. We have x here, right? Whatever, say we're taking this little rectangle right here that we're going to do right here. So this is going to be point x, and this here is going to be point 0. However, we want to rotate it around the line -pi. So this distance is none other than pi itself. So the radius at any given time is going to be x plus pi. So we can go ahead and write x plus pi times this, which gives us our shell in essence. And then now we can't forget our integral. But in this case, we can't use 2 and 0 because we're doing it in terms of x. In this case, we would do 0 to 8 because this point here is 8, 2. So 0 to 8 of this integral. And now the last key part is to make sure you're multiplying by 2 pi on the outside. Now I know that it might be preferable sometimes to take this and bring it to the inside of the integrand, and feel free to do that. I personally just like to leave it out, but you can feel free to do that. And if you work that out on your calculator, it comes out to the same exact answer as the one that we have down here. So if you're getting both the answers using the same exact method, then you're doing it right. So which means that kudos to you, and I recommend you try a few more of these problems, because these problems really, the main way to get good at them is just kind of realizing, like, okay, this is what I'm rotating around, this is my top function, this is my bottom function. So you want to keep all these in mind when doing your axis of revolution problems. Because one little mistake, like say putting the square on the outside or on the inside, can really just mess up your entire answer, and all you can hope for is that your teacher is going to be lenient with the grading. So if you actually have time on the tests, this is only if you have time, but if you have time on the test, I would go ahead and encourage you, go ahead and try both methods sometimes, and that's a really good surefire way of knowing if your answer is correct. And I know that sometimes I do that, but at the same time, you got to keep in mind your time constraint here. So don't go crazy with all these different kinds of methods and then realize that you still have 10 problems left on an 11 problem test at like 5 minutes left. So just make sure that you're keeping in mind your time constraint as well. Okay, so I think that we've established the washer method, the disk method, and the shell method, and that's all there is for solids and revolution. But another topic that's covered this unit is called cross sections. So let me just draw like a basic idea of what I mean by cross section. All right, whenever this line decides to catch up, right there. Okay, good. And go from there to there. Okay, so for a cross section, it's basically just, say you had some curve like this. Sorry, 1 second. So you had some curve like this, and then some curve like this. I'm not even going to bother labeling them because this is purely for visual aid right here. So this is just going to be the area. So what we're basically going to do is we're going to take this green area that we have, right, and kind of push it out of the paper. I wish there was a three-dimensional way of showing this, but I'm not exactly an artist, so I can't draw it much better than this. So for this area, what we want to do is we kind of want to take it and push it off the paper. Imagine these arrows are coming off the paper. And a three-dimensional model would look something like this, giving our x and our y, right? And then our little area would be right here. And then what we're doing in essence is we're pushing this up. And then that's where our cross-section problems come in. Say, for example, if each one was a square, like each cross-section we cut was a square, it looks something like this on the outside, coming out like that. But I know that's not like the best visual model you can have, but it gets you to understand what exactly we're doing here. We're just trying to take this and kind of push it off the screen towards you. So cross-sections do not involve pi, so make sure to keep that in mind, as cross-sections do not involve any form of pi, unless it's originally in the problem. So let's just do a quick example here to illustrate what exactly it is that I mean. So suppose it was just like, I'm not going to give you a curve here, I'm just going to say you have a rectangle, right? Just something as simple as a rectangle. It's not a good rectangle. Rectangle here, right? And we're taking that rectangle, and we're saying that each cross-section of it divided in this direction, the horizontal direction, is going to give you, for example, a square, right? So it just means that you're going to end up with something that looks a little bit like this. That's going to be your top. And then like this on the bottom, like that, and then you have your little imaginary lines on the inside. And each one of these is going to be a square. And that's just in essence what a cross-section is. And then you use various types of formulas to determine what the volume is. Like, for example, if it was a semicircle, in this case you would have pi inside the integral for the solids of, sorry, for the extrusions and the cross-sections. But if it was just like something like a rectangle or a triangle, for example, you wouldn't bother with that because there's no need for pi. So let's go ahead and go back to our original problem, actually, the same exact problem we did last time. And let's see if we can do some extrusions with it. So let's go ahead and draw our axes yet again. There and there. So our problem last time said that we had two curves, right? One of them looks a little something like this. Oh, goodness. Okay, here. A little something like this. And our other one looks a little bit like, not blue, green. A little something like this. Oh, well, that wasn't green. Okay, whatever. So a little something like that. And we want to find our green area right here. But suppose that I was to push that area off the paper now, and I'm asking you to find cross-sections for it. So let's go ahead and try that. So suppose that each cross-section of this is going to end up being a square if I was to slice it this way, like parallel to the y-axis, like this, downwards. Each cross-section is going to give me a square of this. So in essence, what I'm saying is the distance between these two is going to be equal for all the cross-sections that we decide to slice on. So the height and the distance are going to be the same. So let's go ahead and set up our integrand again. So in this case, we would have, this is our y equals x over 4, and this is our y equals x to the 1/3. So to begin with, let's just go ahead and establish what our base would be. Our base is always going to be with whatever rectangle we decide to fit in here, like this little rectangle right here. Whatever rectangle it is we decide to fit, that's going to be our base. So our base in this case is x to the 1/3 minus x over 4 for any given point. That's just any given. This isn't a summation yet. It's not integral. It's just, I'm just saying this is going to be the base. Now, if each cross-section is a square, right, we know that for squares, the base and the height, right, the base and the height are the exact same. So in this case, you'd be multiplying by this quantity again to get you the kind of the height of this little square that's projecting off of the screen right here. So we would just square this basically because base and the height are the exact same. And that's just for one of the squares that we're going to do. But say, for example, we were going to try to do every single one of the squares from this point to this point. That's where our integral comes in, because integrals are infinite sums. So I'll write this in a different color here. So our integral, okay, would go from the same values. Now, since we're doing this with respect to x, we would have to use the x values for our upper and lower bounds right here. So our lower bound is the same as 0, and our upper bound is the same, which is 8. If we were to do it using y's, then this would be a completely different problem. So you got to keep in mind what your bounds are going to be. So this would be from 0 to 8 of this thing squared dx, and it's really as simple as that. See, there's no pi involved. There's no like really crazy like x minus k thing kind of involved. It's just this quantity squared when you're dealing with squares actually, because it's the same exact length. So when you do work this out, I encourage you to go ahead and try it as well. But for the sake of time, I'm just going to tell you what the answer is. The calculator syntax, I'll just go over the calculator syntax. So the calculator syntax for this problem, say that you let y1 equal x to the 1/3 and y2 equals x over 4. So all you would do is you would say integral of, parentheses, y1 x minus y2 x. And then now, you gotta be careful here. Make sure you put quantity, right here, quantity squared, because we're squaring this thing here. And then you would do comma x, which just means you're taking it with respect to x. And then you would do comma your lower and your upper bounds. So 0 and 8 in this case. So it's going to give you 0, and it's going to give you 8, and then close parentheses, because calculators don't do it if you don't close the parentheses. Okay, so this works itself out to be something quite manageable, actually. It comes out to be 256 over 105, and you are welcome to verify that. And if you keep getting these kind of problems right, then you're in good shape. But that was a rather simple one, so let's try just a slightly more challenging version of that problem. So suppose that instead of getting a square each time we slice this thing, we were getting a semicircle, a perfect semicircle. Okay? So in this case, we have to consider, well, what are our properties of a semicircle, right? So basically, this right here, the height of the semicircle, right, in essence, is just going to be the same as the radius of the semicircle. And the radius is 1/2 times the diameter of our semicircle. Okay? Now, what is the diameter of our semicircle in this case? The diameter of our semicircle in this case would be top minus bottom. So you can clearly see that top minus bottom thing continually surfacing itself over and over again. So that's really crucial for this test. You have to understand top minus bottom. It's always going to be top minus bottom. So x to the 1/3 minus x over 4. So let's just write that down here. This is our base. X to the 1/3 minus x over 4. That's going to be our base. But now we're going to ask yourself, okay, what am I going to do with this base? What is the formula for area of half of this? So the area we know of a circle is pi r squared, right? So pi r squared. But in this case, we're looking for half of this. So 1/2 pi r squared is what we're looking for. So now that we know it's 1/2 pi r squared, we can just work this out. And if you work this out with the diameter, because the diameter is going to be this rectangle we have right here. So it's going to be 1/2 times the diameter. So basically 1/2 pi times 1/2 diameter, right? And then our diameter is squared. So in essence, it's just pi times diameter squared over 4, because 1/2 pi r squared is going to give me the area of this, but our r itself is 1/2 times the diameter. Now our diameter is this, which is the same as our base, because it just rotates around in a circle. It's the same exact thing. And then what you would have to do is you have to put that 1/4 next to it, because you're multiplying 1/4 times this to get the diameter. And then you can go ahead and put the pi on the outside of the integrand. I just like to put pi on the outside. You're welcome to put it on the inside, but I just put it on the outside for clarity's sake. So 0 to 8 of this integral right here. And then what you would do is you make sure you square it. But see, this is where most people would make a mistake, would be they just put the squared here and then put dx here. But in fact, that's not correct, because this thing has to be squared the entire quantity, because you're not squaring just this and multiplying by the 1/4, because then that's a different problem. What you're doing is you're squaring 1/4 times this. This is what you're looking for. So this is what it is in fact. So this is what it comes out to. Now I'm actually going to leave this answer up for grabs, because I'm not going to disclose this answer. What I'm going to do is I'm going to see if you guys can solve it, and if you do end up solving it, go ahead and message me or let me know, and in the next video I'll let you know who was able to solve this problem. So I'm just going to leave this out there for now. Let's consider it the simplest challenge problem. So that's going to be the area the volume if we were to cut a cross section of it using the extrusions. So keep in mind, for all kinds of extrusions, this would just be anything. You just simply pull this out. Give you a better visual here. It looks like this and this. So by pull it out, I mean, in this case, looks something like this, and it's going to be coming up out of there. And then just if you can visualize this well, then you're in good shape for the test. So this at any point you can slice it anywhere you want. You can get triangles, you can get semicircles, you can get some really wacky thing that whatever your math teacher tries to throw at you. But if you just keep this in mind and keep the whole symbology of like top minus bottom, keep that in mind, you should be perfectly fine for these kind of problems. Like there's not really much of an issue. Okay. Right. Okay. So thank you really quick. I just want to correct something I did really quick here. So for r squared, right? We established that r squared is going to be 1/2 d, and I actually did make the mistake here. 1/2 d is actually the quantity squared, so we have to keep that in mind. So this actually becomes 1/4, and this becomes 1/2. So this actually integrand is going to change. This is going to become the integrand from 0 to 8 of pi times 1/8 x to the 1/3 minus x over 4 squared dx. So thank you for that. I was actually corrected by a viewer, so thank you very much for that. And that's a good catch there. See, I made that mistake there, and you just have to keep in mind where you want to keep your squareds on the outside. And this right here should give you the right answer for the integral. Okay, so keeping that in mind, I think we've established a solid foundation with cross-section. So let's just move on to our final topic for the night, which is going to be arc length. So for arc length, let's go ahead and derive the formula to start. So suppose we have something going like no, okay. So here to here, that's going to be our x. Here to here is our y. So suppose we have something like this. Oh, I always do that. Right like that. Okay, so what we want to do is we want to find the length of this curve. Now, it's really hard to find lengths of curves because, well, they're curved, so it's not straightforward. Like if I just give you a line, that's easy, right? You could find the length of the line pretty easily by breaking it up into its segments and then using Pythagorean theorem, right? So just x, this is x and y, it's just x squared plus y squared, radical of that, like that. Okay, and that's just going to give you the volume, sorry, not the volume, the length right here. But in this case, we don't have something as neat and easy as that. We kind of want to figure out, well, how are we going to get that? So let's draw our point P and our point Q, for example, okay? Point P and point Q. So let's just see if we want to find the distance between P and Q. That's nothing but distance formula itself. The distance formula says that the distance between any two places on a line is going to be x2 minus x1 squared plus y2 minus y1 squared. Okay? Now, this x2 minus x1, right, is just the coordinate x of P and Q, and the y2 minus y1 is very similar as well, x2 minus x1, y2 minus y1. So we can rewrite this as delta x squared, correct? Because it's just delta x just means change in x, and then this is just going to be our change in y, delta y squared. Okay, so that's going to give us our distance between P and Q. So right here it goes d between P and Q, d is distance, equals that. Okay, so now let's manipulate this a little bit. Let's just see if we can go somewhere with this. So if I was to pull out a delta y squared, okay, there's actually two ways of doing this. I'm going to do it my way first, and then I'm going to show you the way that my math teacher showed me. So my way would be to pull out the delta y squared, just factor it out. So you get delta y squared, right, and this is all inside the radical, times. Now if I was to pull out a delta y squared from delta x squared, I would get delta x squared, right, divided by delta y squared. Okay? And then, in the other case, I would just get 1, because I'm just dividing by the same exact thing. Okay? So this is our change in x by our change in y. Keep in mind, it's change in x over change in y, not change in y over change in x. Change in x over change in y for now. So delta y squared times this quantity. But now, using properties of radicals, we can just pull this out to get delta y times delta x over delta y. But now, once again, using properties of exponents, I can put the squared on the outside and then just add 1. So that's going to be our original formula for just the distance between P and Q. But now we want to ask ourselves, okay, well, what's the formula between for everything, like between every single line. So that would just be like an infinite sum, right? So let's pick length between, say this is just A and B now. I'm going to call it A and B. Length between A and B equals, right? So now this is where we incorporate the summations. Actually, I should write just for notation's sake. This should be approximately equal to, not equal to. Approximately equal to the sum, right, from this thing right here. So delta, so it's going to be radical 1 plus delta x over delta y squared times delta xk, I believe, right? Delta x of k. Good. So when I say delta x of k, I simply mean increments of delta x. So this is k, distance between them. I'm just substituting that in to let you know like what exactly it is I'm doing. And this is actually delta y of k, my bad, delta y of k. So that's just the increments of what I'm doing on the y-axis this time, increments. Now I'm going to take this from, say, I equals 1, just I is an arbitrary variable, I equals 1 to n, okay? But that's just the approximate area. We want the exact area of this thing now. The exact area of this thing would come out to, now I'm writing equals, not approximately equal to, equals, because it's going to be the integral from a to b of radical 1 plus. Now, if I was to take the exact area, right, delta x shrinks infinitely small. Delta x shrinking infinitely small becomes dx. And similarly, delta y shrinking infinitely small becomes dy. So this becomes dx dy squared. Okay? And that's what this integrand comes out to. And then we have a delta y on the outside. Delta y, as I said, becomes dy. So this is what this becomes. And this is just, I wanted to emphasize that this is delta x over delta y just to show that this is my method of doing it. And now I'm going to show you my teacher's method of doing it. Because typically the conventional formula looks like this. It would be arc length equals integral from a to b of radical 1 plus dy dx, right? I chose to do dx dy this time just to prove a point that me factoring this out was a slightly different approach than what, for example, my teacher did. So I'm just going to show you the other approach right now using dy dx instead of dx dy. So starting at this step right here, right? The other method, it's actually identical to what I'm doing, except the syntax is just slightly different. Is you in essence just multiply by delta x squared right here, delta x squared, and right here this becomes delta x squared plus delta y squared, like that. Now if I was to multiply this by delta x squared, well, that's not allowed because I'm multiplying by, I'm changing this function, so I want to multiply by 1, so I'm going to divide by delta x squared as well. Okay, so this basically just turns into delta x squared, distance between P and Q, and this becomes delta x squared. The square root of delta x squared is just delta x, and the distance between delta x squared and delta y squared is going to be divided by delta x squared. So this just becomes 1 plus dy dx squared. So delta y over delta x squared, like that. Okay, and then this is just a slightly different method of doing it. So now that both methods are equally valid, I would actually recommend you use this method, but just to show you how I did it, I used the different one. So delta x, you pull this out, this is what you get, and then this turns out, when you use the same exact summation notation, to this formula up here, okay? And I was actually pointed out real quick by a viewer that a to b is actually incorrect when doing this length because I'm doing it in terms of dy. So I would actually have to do f of a and f of b. So this thing right here for our integrand here is going to be f of a and f of b because I'm doing it in terms of y, not in terms of x. So that was an important point, and I thank you for bringing that up. So this right here is how you derive the formula on any kind of exam. And these two are the same exact thing, but just to show you that this one is different, this is dx dy squared. Make sure you don't do dx dy squared on your test because traditionally it's dy dx because that's the known derivative. But dx dy is equally valid. However, this is something that they're not looking for when they ask you to derive the formula. Okay, good. So moving on from there, let's see if we can do a quick practice problem with dy dx and using the whole arc length formula thing. Now I'm going to go back to the same exact problem that we did last time, the same exact one, because it's a good problem. It's a good problem. Okay, so this goes down this way, and this goes down this way. We have our regular x to the 1/3 curve, looks something like this, and our regular curve looks something like this. Okay, that was I'm not even gonna, that was a bad lie. I'm gonna try that again. Okay, so it goes like that. Okay, so this becomes this there. Okay, so now what I want to do is I want to find the perimeter of this thing. The perimeter, right? How do I find the perimeter? Well then, let's see. How do we find the perimeter? Well, we have our formula right here. So let's go ahead and see if we can use that, right? So x to the 1/3 and x over 4 is this function here, and we're taking it from 0 to 8. Okay, so let's start with x to the 1/3 because this is basically going to be, say this is perimeter A and perimeter B. It's going to be perimeter A plus perimeter B. Okay, so perimeter A is going to be the integral from 0 to 8. Okay, of radical 1 plus. Now dy dx of x to the 1/3. Okay, this is going to be, we're going to use the power rule here. So you bring the 1/3 down, and then you subtract 1/3, sorry, 1 from the power to give you x to the negative 2/3. Right, so this is 1 over, actually I'll leave it like this for now. 1 over 3 times x to the negative 2/3. But then we're keeping in mind that we're squaring this here. That should be a square. Apologies, that should be a squared up there. So now we're squaring this. And if we square that, it comes out to 1 over 9x to the 4/3. And how I did that was just bringing this down. So because 2 times negative 2/3 gives you 4/3, and I brought that to the denominator, and 1/3 squared gives you 1/9. So that's what this comes out to. And then obviously dx, right? Yes, correct. So that's from 8 to 0 of this. And that's going to give you this length right here. Now we want this length here. Now this length is actually interesting because we can take two different approaches for this length. I'm going to use the arc length formula here just for formality, but it's interesting to note that we actually don't need that formula here because this is just a right triangle with 8 and 2, right? So we just go ahead and putting it to the side. That actually would work itself out to 2 radical 17. Just putting it to the side just by using Pythagorean theorem. However, let's go ahead and exercise the arc length formula again, just for being consistent with what we're doing. So this would once again be the integral from 0 to 8 of radical 1 plus. Now dy dx squared, right? So what's dy dx of x over 4? X over 4. I can rewrite x over 4 as 1/4 x, right? And then 1/4 is simply the derivative of x because that's the slope of the line. So 1/4. I'm just going to put that there. And it's just the 1/4. There's not even an x in this one. Just 1/4 squared dx. Okay, so that's what this works itself out to. And then if I just add these two integrals, I'm going to get my answer. So let's just see what this one comes out to just by hand, just to confirm that we're doing it properly. So 1 plus 1/4 squared, right? Well, 1/4 squared is 1 over 16. 1 plus 1 over 16, right? So 1 we can rewrite as 16 over 16 plus 1 over 16, which works out to 17 over 16. Radical dx integral of. Now what we can do, since this is just a constant, right, we can just go ahead and pull that out because we can pull constants out of it, and we can actually simplify as well. Radical 17 and radical 16 becomes just 4 times 0 to 8 of dx. Now the integral of dx is simply x, so I'm going to rewrite that over here real quick. So this right here, this integral right here just becomes radical 17 over 4 times x from 8 to 0. Okay, so now if I plug in 8 for x here, I get radical 17 times 8 over 2. I'm not going to bother plugging in 0 because that's just going to give me 0. And the 8 and the 2 can simplify, sorry, the 8 and the 4. The 8 and the 4 can simplify to give me 2, which works out to 2 radical 17. Okay, so that's the same exact as this one here. But if you just stop the problem right here, you would actually be wrong because what we need to do is we need to find the perimeter of this entire figure. So what you would do is you would add these two areas. Now this one is can't be done by hand completely because you can't raise 8 to like certain powers you get when you integrate this. So this is the calculator one right here. And if you add 2 radical 17 to this, it works itself out to give you a perimeter of approximately, I'm going to make sure I write approximately, 18.7434. Okay? 18.7434. Now you're welcome to go ahead and verify that, and I actually suggest that you do, just to make sure that this problem is correct. And this is just the arc length formula. It's very straightforward. All you do is simply plug in and you chug, and you just plug and chug, and it gives you your answer. There's no special kind of properties involved. And this case was even simpler actually because it's just a right triangle, and we verified that it actually does come out to the same thing. So that right there actually wraps up the immediate new stuff that we're going to be learning. But what I'd like to end my videos with now is going to be a quick challenge problem that kind of tests your abilities for not this unit actually, but it'll test you for the next time we decide to meet. So real quick before that challenge problem, let's do a quick wrap up of what it is that we established, right? We had established the area bounded between two graphs, which is simply the integral from a to b of f of x minus g of x dx, right? That is the area bounded between two graphs. F of x is upper, g of x is lower. And then for the solids of revolution, what we had done was the disk method. The disk method was pi times the integral from a to b of f of x quantity squared dx, right? And then we'd also done the washer method. The washer method is the integral from a to b of pi times, right? This becomes f of x quantity squared minus g of x quantity squared dx. Okay? Once again, just assume there's a bracket there because there's not enough room to draw it. But this is the washer method. And keeping in mind, for all of these, I'm just going to write on the side, for every single one of these, f of x is outer and g of x is the inner. Okay? The other thing that we had established was the disk method. Now this was not necessary because it's not on the problems, but it is extremely useful. And the disk method is the integral from a to b. This time it's going to be 2 pi. I'll put on the inside because so that we know what method is we're doing. Times x times f of x. Now keep in mind, this x varies greatly depending on what axis it is you're revolving around. It's only x if you're rotating around just the y-axis. It changes y-axis. It changes if you're rotating it around some line x equals k, right? Just keep that in mind and you should be good. And the last thing that we'd established tonight was the arc length formula, and we derived it as well. 1 plus dy dx squared, right? The integral of that from point A to point B dx. Now keep in mind, I did do it both ways for dx and dy, but it is going to be dy dx. And this, I do mean the cylindrical shell method, just to clarify here. This is the cylindrical shell method, and this is going to be the arc length formula. So make sure you put dy dx on your test and not dx dy, unless of course you're doing horizontal rectangles. If you're doing horizontal rectangles, then you can go ahead and do dx dy, but for most times it's just dy dx squared. Okay, so that's a quick wrap up for the test. Just keep in mind, tips for the test would be, before you even approach a problem, just make sure that you know exactly what it is you're going to do. So, for example, if you see a problem, don't just go head on tackle it, think I got this, because you may get it right, but it's more important that you get your approach down first, because more points are awarded for having the right approach than actually having the right answer in itself. You might even have the right answer, but if you have the wrong approach, then you might even get points off. So just make sure that your approach is correct. Know which one is the correct approach, and most of all, be efficient with your time. Because if you try to use, like, for example, the washer method right here, this is the washer method, when the cylindrical shell method is perhaps much better, then you'd just be wasting time that you could be doing on something else. So those are just some tips to keep in mind for when time the test comes. And now I'd just like to wrap it up with a few challenge problems. So if you are just solely studying for this test, you may as well just end the video here, because these problems will not be focusing on this test. Rather, they'll be focusing on the time that we decide to meet next. So the next time we decide to meet would actually be covering Hopital's rule and indefinite integrals. and after that, sequences and series. So I'm going to give 2 challenge problems. So challenge problem 1, okay? And for the record, I do design these by myself. So if you try to Google them, I am afraid you will not get too many results. If you do, then I mean, I guess that's lucky, but I do design these problems by myself. So I hope that they are challenging and thought-provoking. So I'm going to define 2 series here. This is for our series and sequences problem. R to the b plus r to the 2b plus r to the 3b dot dot dot. Okay, so this is our series right here, and I'm going to ask you to find a over b. Okay, and this is little a over little b, not big A over big B, little a over little b. Find that answer for me and see if you can get that. That's the first challenge problem. And challenge problem 2 actually deals with Hopital's rule. Take the limit as x goes to infinity of natural log of x squared plus 1 divided by x plus radical x. Okay? And these are 2 challenge problems. This one's not terribly difficult. It's just a bit tedious to execute. However, this one does involve a little bit of outside the box thinking, and kind of like you got to know like what it is you're doing with sequences and series. Now, I actually don't expect most people to know the answer to this one because we haven't done sequences this year yet. But I will tell you one tip for this problem is that there's absolutely no calculus required for this one. I mean, if you find some way, then go ahead and do it, but there's no calculus required for this one. For this one, however, there is. So there's no calculus required for this one. It's more of just a review. Okay? So I'd like to thank you all for watching, and hope that next time that it'll be as helpful and that you are able to do better and better on these tests as you keep watching. So I would like to conclude by saying that, let me see here. Give me one moment. Okay, so thanks for watching, guys, and I hope that this video was helpful. I hope that it was thought-provoking, and most importantly, I really want your feedback on this problem, and I want your feedback on how I did overall. Let me know if there's anything I can change, anything I can do to help you maybe tackle these problems better. Just anything at all. Any advice is good. Just go ahead and let me know either on Facebook or on comments, and I'll do my best to change it to help you guys out, all right? So thanks a lot, and I hope to see you again soon.
All right. All right, can everyone hear me?
Yeah, we're good, Rahul. We can hear you.
You can hear me?
I can hear you.
All right, so I want to wrap up this video. I hope you guys learned a lot of calculus for this test that's coming up. I hope Ganesh did a good job. I trust that he did. Hopefully, you guys will do well on your tests, and I think, as Ganesh mentioned towards the end of his session, to give him any feedback, give us any feedback. If you have any questions for him, you can either message me, message him about it, and we will get back to you as soon as possible. But other than that, thanks everyone for watching. If you like this, make sure you subscribe to our channel. And just a heads up, if you're watching right now and you're interested in finding out when the next AP US History video will be, it will be on, I'd say, Thursday around the same time, so that everyone will be ready for the test. If you want us to do it earlier, just let us know. But if not, thank you everyone for watching. All right, see you later.